Okay, in this session I would like to talk about 2D groundwater flow governing equation, but before going through the detail of a 2D system, I would like to briefly review what we did in the last session. So if you remember, in the last session we said that we can write the 3D groundwater flow equation as partial x kx partial phi partial x, similar term in the y direction, ky partial phi partial y, and this similar term in the z direction, partial z kz partial phi partial z, plus a sink and source term. So you should be very careful with this term because we already talked about this, and we know that physically it means the volume of water which can stored or released from the cubic meter of the aquifer per unit time, for example day. And the right hand side, we say that we can write the right hand side the accumulation term using the specific storage term partial phi partial t. So this was the pretty much a comprehensive form of groundwater flow equation in the 3D system. But I would like to define a terminology here that we're going to use to convert this 3D system, this 3D equation, into a 2D system. So which is a very practical simplification. So you'll see why in a minute. You know that we briefly a little bit talked about this. So we said that technically, for example, if this is my confined aquifer, this is the upper and lower confining layer, I would say that, for example, I would assume that the water flows as what you see here. So these are the streamlines. So water flows in a parallel form. So all the streamlines are parallel, and for example this is my x direction. So they can this would also happen in the y direction, so everything can go parallelly into the screen or out of the screen, but the only thing that you won't see is the vertical flow. So it means that there is no vertical flow in this system, but the water can move in the x and y direction, but in a parallel form like this. So it means that, for example, the streamline is not something like this, or it does not something like this. So in this situation, you know that mathematically you can say that in this case the partial phi over partial z is 0. So for example, this is my z direction, for example. This is my z-axis. Okay, so technically you know that you can go and measure the flow rates, for example the q in the x direction, using this formula. We already talked about this. Qx with times. So for example, if you're interested to find so for example, this is the thickness of, this is the width of the aquifer, and this is the thickness of the aquifer. So if you want to know, if you want to find the flow rate in the x direction which passes through this cross section, you can find it by this formula, qx times w times b. Okay, but if you look at the textbook, you will see that if I assume that there is no vertical or the z direction flow rate, I can define another term, which in the textbooks they use it usually by Q star as Qx times B. And what is this? This is actually called the depth average Darcy flux. So if you look at the unit of this, the things will be much more clear. So the unit of this, is the volume of water which passes through the unit area per day, right? But Q star is the volume of water which passes through the unit width of the aquifer, thus W. So the unit width of the aquifer per unit time. So technically we said that the Q is the flow per unit area, and Q star is flow per unit width. And similarly, you know that we can define the transmissivity in the x direction, which is the Qx times B, and its unit is meter square per day. Okay, now I would like to use the Qx terminology to derive the 2D governing groundwater governing equation of the groundwater flow. So to do that, if you remember, in the 3D system, if this was, for example, my control volume, okay, so I assume that technically I can go and write the mass in minus mass out equals accumulation, right? But now I used or I defined a term, or technically I averaged the depth averaged the flux in the z direction. If this is the x, if this is y, and this is my z direction. So technically I assume that everything is parallel, and there is no z direction gradient in the system. So assuming this, I can simplify my control volume into a 3D form. So technically now I can have a plane form of control, technically a control area. Okay, so because I know that actually what's happening in the z direction. So in this condition, so if this is, for example, my this was x, so technically this will be my delta y, and this is my delta x. I want to find the Qx, so now technically the mass in which can go into the system is the Q star at x. This is the rho. I multiplied rho just to turn everything into the mass form. So the Q star at x plus delta x. Here, this is rho Q star y. This is at y plus delta y. And this is rho Q star y at y. Pretty much the same concept. But the other difference in the 2D system that you need to think about is that there we have the sink and source term, which was the cubic meter per unit volume of the aquifer per day, but in the 2D form, so we turned 3D system into the 2D system, right? Now we convert W to N, which its unit is, this is again actually a sink and source term, but in the 2D form. But now this is the volume of water which gets released or stored within the unit area, because I know that actually what's happening in the z direction per unit day. Okay, now I just want to do a mass balance calculation, similarly what we did in the x direction, so, in the 3D form. So now I want to find the mass in minus mass out, which equals with accumulation. Okay, so in the x direction, so I want to just very quickly calculate this. So in the x direction, you know that you can write rho q star, q star let me see how I can erase this. Yes, so q star in the x direction minus q star at x plus delta x times delta y delta t. Okay, and similarly, so this you can simplify this into rho q star x at x plus delta x minus q star at x rho delta y delta t. Okay, so similarly you can write a similar thing in the y direction. In the y direction you can write a similar thing in the right direction, and now everything will be q star y at y plus delta y minus q star y, y rho now delta x delta t. Okay, so this is kind of the left hand side, the mass in minus mass out, and as you can guess, we can write the accumulation term. So the accumulation term can be written, so we show it with a delta m. So now we can say that the delta m is, now we use the parameter, the capital S, delta x delta y times rho. Now the head changes. So we already talked about this and we solved a few examples, and I think that actually you know exactly what I'm talking about. If it is not clear, you need to come back and look at your notes and review the specific storage coefficients and SY. So these were the three important storage coefficients that we talked about. So we said that this is a 3D, this was a 3D property, and this was a 2D property. Anyway, if you use this equation, technically you can write the accumulation as what you see here. Okay. The other parameter or component that we need to think about is the sink and source term. Okay, so we said that we use the sink and source term as N. So that the volume of water which can stored or released from the system can be calculated as N delta X delta Y rho delta T. So this term is technically the amount of the volume of water which gets released or stored within the unit area. This is the mass. So this is the mass of water, the kg of water stored or released from the delta x, delta y area during delta t. Very similar to what we did in the 3D system. If you write the in minus out equals accumulation formula all together, and if you divide everything, the left and right hand side, by rho delta x, delta y, and delta t, eventually you can see that everything will look like this: the q star in the x plus delta x minus q star in the the qx at x divided by delta x minus q star at y plus delta y minus q star, the qy at y plus delta qy at y divided by delta y plus n equals s delta phi delta t. Now, if you limit delta x, delta y, and delta t to go to 0, you can convert this and use the partial symbol. So you can say that this will be negative partial q over partial x, star, negative partial q star, this is in the x direction, this is in the y direction, y plus n s partial phi partial t. Okay, so now you see that now this is the partial differential equation form of a mass balance in a 2D system. Right? So now everything is in the form of Q star because these are the depth average flux, right? So we already talked about this. So we know that the Q star x, and if we want to convert, technically we know that the Q star x is nothing but the Qx times B, right? So, and the Qx is negative Kx partial phi partial x times b, right? Similarly, I can write the similar things in the y direction, right? So if I want to write it here, so the q star x is negative, you need to, or don't forget to put negative tx partial phi partial x, and tx, you know that it's nothing but kx times b, right? So, and q star y is negative ty partial phi partial y, and ty is ky times b. So now using this, I can write this this equation Okay, I can write this equation as partial x, tx, partial phi, partial x, plus partial y, ty, partial phi, partial y, plus n, s, partial phi, partial t. So this is a 2D confined flow equation. And remember that actually everything that we're talking about today and in the previous sessions, everything is in the confined system. We're going to talk about unconfined system in the next session, which is kind of a 2D flow. We are going to talk about this later. But what we're talking about here in this session, everything is in the confined form. So this was, for some reason, I want to use or derive the 2D equation this way because I wanted you to think that technically you can. It's very, very important to note that the 2D concept is valid if this is valid. The partial phi over partial z is 0. So it means that this is valid if you assume that your flow, your streamlines are parallel in both x and y direction. Okay, so which is a very we're going to talk about this later because it's a very valid assumption because technically you know that if this is your problem, technically if you want to correctly scale your model, so your aquifer would look like this. So this is in the order of, for example, let's say 100 meters, and this is in the order of, so still I think it is not scaled, but this is, for example, 10 kilometers. So this should be 100 times longer than this, which is still, it is not, but maybe I should have so maybe if this is the upper layer, so maybe this is your confining layer. And now in this situation you can assume that it is fairly reasonable and acceptable assumption to assume that everything flows like this. So you technically neglect whatever would happen like this, which is very minor. So for example, the water would flow like this, but the you can assume that this is a straight line. But remember, this can happen both in the x and y direction, but not in the z direction. Okay? 2D from 2D governing equation from a 3D equation. So if I write the 3D equation like this, so this, if this is kx partial phi partial x plus partial y, ky partial phi partial y plus partial z, kz partial phi partial z plus w s sub s partial phi partial t. So technically if I assume that the partial phi over partial z is 0, and if I multiply everything by b, so technically this will be partial x tx, right? So you know that kx times b is tx, right? So tx partial phi partial x partial y ty partial phi partial y. This is 0, and w times b, again w times b equals with n. Okay, we represented it with n, and s sub s times b is capital S, right? So s partial phi partial. So this is another way to look at a 2D equation, which is mathematically right, but you need to be very careful and I wanted to do the 2D system differently using the QX concept, because the concept of Q star, which is the depth average flux, is very important. I've seen that so many students have difficulty with this, and this is a very fundamental concept that you need to learn. But you can keep going and derive a 1D groundwater flow equation from the 2D equation. Okay, so if you look at this equation, let me see if I can copy paste. Yeah, it seems that I can copy this equation. There you go. So if this is the 2D equation, now I can assume that partial phi over partial y is 0. So it means that in this system, if this is my x and if this is y, everything is in the x direction. So the water cannot go into or out of the screen. So in this situation, I can write the 1D system as partial x, partial x, tx, partial phi, partial x. This term is 0, and s partial phi, partial t. Okay, so this is the 1D groundwater flow in a confined aquifer. So I'm going to assign you some homework problems because I want to practice a little bit with the governing equation and analytical solution, but you're going to just work or practice a 1D groundwater equation, which is the simplest form, and you will see that you can solve very interesting and practical groundwater flow problems. But we said that, so let me rewrite the equation here. So I'm going to try to write things smaller. That would give me more space. Okay, so this is the transient form of a 1D system. And you know that you can even simplify this, and if everything is in the homogeneous system, this is constant. It means that the tx does not change with x. It is a constant value in the entire space domain. Technically, we can take this out and look at it as tx, the second derivative of phi, x squared plus n is partial phi partial t. And if the system is even in the steady state condition, it means that partial phi over partial t is 0. So then it means that the steady state 1D steady state flow can be mathematically be represented by this equation. Very beautiful. Okay, so let's go and solve an example problem to make practice this equation. Oh, by the way, you know that actually mathematically to solve, for example, to solve this specific problem, you need to have this is the second derivative with respect to x. So it means that at least you need to have 2 boundary conditions Do you need an initial condition? No, because you already assumed that the head won't change with t. So for the steady state, you don't need to have an initial condition. But if you wanted to solve a transient solution for the groundwater flow, if this term is not zero, technically you would need, definitely you will need an initial condition. Okay, so let's go and solve an example. So in this is the example problem that I would like to solve for you. You have a river. So this is my aquifer, and there is a big lake here. Okay. So the river here, the stage of river is like this, and the stage of the lake is there, and there is a confining layer an aquifer like this here, another aquifer like this here. So there's a confining layer here, and if you, so I don't want to have for the first let's work on this, and then I will actually make this problem a little bit more complex. So in this situation, you know that if you are looking at a steady state condition, so technically this problem is identical with this problem, right? That actually we already solved, I think, in homework 3 or maybe in homework 2. So it is pretty much like this problem, but I just, instead of now, let me see how I can erase this. Okay. Oops, I had to erase this guy. So this is lower, this is lower, this is higher, and in the steady state condition, you know that if you want to find the profile, if this is my x0, if this is my x, for example here, this is x equals 0, this is x equals, for example, I don't know, 2,000 meters, 2 kilometers away. So now if this is the steady state condition, you know that, if this is a steady state condition, technically you know that the head profile is the straight line, and you can go and find the head at each position, and you know that in this specific case, this is the lake which contributes water into the stream. So if you want to look at this problem, so this is the plane view. So this is the river, and for example, this is the lake there. Now you are looking at this section of the problem. So for example, now you want to know that how much water gets into, what is the interaction between these two surface water bodies. Okay, so okay, to play with this problem, you know that the system is in the steady state condition, partial phi, partial t 0. So then it means that you can use, and it is suppose that it is a homogeneous system. Okay, so you can say that the tx partial, the second derivative of phi with respect to in the x direction plus n equals 0. So in this specific example, we assume that there is no so let me actually assume a recharge term here. So in this specific problem, now if there is no recharge, this water, the right hand side boundary condition is greater than the left hand side, and definitely now you know that the water would move from the lake to the river. Okay, but if there is a recharge, the things will be a little bit more interesting. So if rainfall happens here, or for example, instead of rainfall, let me assume that this or that would be rainfall, or for example, there is this is my tractor, for example. So this is the farmland, and actually they irrigate this area, okay, and the water gets into and get accumulated here, and eventually you have a little bit of recharge on top of this aquifer, okay, into this aquifer. So in this specific case, you know that now the head is not in a straight line anymore. So technically what happens, you will see in a few minutes that actually mathematically you'll see that the groundwater head will mount a little bit. But how it mounts, we don't know. Everything depends on the magnitude of N. So it means that if you have a rainfall here, it's very interesting. I mean, look at this problem. So if the groundwater mounts here, it means that you will have a divide here. So it means that if you are actually, I don't know, the water is contaminated by the products that you use in the farm or whatever, if it is contaminated, you know that this amount of water which gets into this, now they come back to the lake, and the water from here come back to the stream, and now the water cannot, now the lake does not contribute anything. It cannot, because the head here is higher than the lake. So technically now the lake cannot contribute to the system. So things would change if you have a recharge. But how you can handle or solve this problem and figure out what happens, you can look at this equation. Okay, so to solve this equation, you have two boundary conditions, right? So at x equals 0, the phi at x equals 0, so let me write it, phi at x0 or phi at x0, so I can write it here, is phi 1, this is the stream level, at x equal L, the phi at x equal L is phi 2. So I have two boundary conditions. Now if I integrate twice from this equation, so I integrate once, now this will be, before doing that, so for some reasons, to make things simpler, I would like to take n to the right. Okay, so this will be partial, the second derivative of x minus n. So I just took n to the right and divide it by tx. Okay, just to make things simpler. And for some reasons that you're going to see later, I just want to rewrite n over tx as alpha. Okay, so this is just a mathematical notation. Okay, now I want to solve this problem where alpha is n over tx. Let me go and write this. Let me see if I can Yes, I can. Let me. Okay, that's enough. So, okay, so I want to solve this problem. Okay, so now I integrate once. If I integrate once, I can rewrite this as partial phi partial x negative alpha x plus c1. Agree? And if I integrate again, I can write phi, which is a function of x, right? Phi x as negative x squared over 2 plus c1x plus c2. Okay, so this is the analytical solution of this problem, the 1D steady state problem for that stream lake example problem. So if I plug in the boundary condition information here, I can let me find a solution for you. So if at x equals 0, I know that the phi 0 is phi 1. So if I plug in this into this equation, so it means that phi 0, I just put x as 0. Phi 0 is this term will be 0, this term will be 0, only c2 will remain. This equals phi 1, so it means that c2 is phi 1. This is the one unknown that I had. So similarly at xl, I know that the fl is phi 2. Now if I just plug in l into x, this will be negative alpha l squared 2 plus c1l plus phi 1, and eventually c1 will be alpha l2 plus alpha 1 alpha 2 alpha 2 minus phi 2 minus phi 1 over L. Okay, so this will be C1, and the final the analytical solution for that specific problem is phi x is phi 2 it is negative alpha x squared 2 plus phi 2 minus phi 1 over L plus alpha L 2x plus phi 1. Okay, so now you see that, as we discussed before, now you see that the analytical solution for the steady state, the profile of the groundwater head, now it is in the form, it is not in a straight line, it's a quadratic equation. So it means that the water mounts like this, okay? And technically you can go and find the maximum of the profile. So if this was the river and if this was the lake, so the groundwater profile mounts like this. And technically you can go and find the maximum of this, the maximum of the head between these two surface water bodies. And how you can do that? It's very simple. I mean, based on the mathematics we've learned in the high school, we know that we can find the maximum of a profile, but just putting what? Partial phi over partial x equals 0, right? So this will give me the point at which the x at which the head is maximum. Okay, so I can do it differently. I can go and directly again find the first derivative of this equation, or if you go back, you will see that we already calculated it somewhere here. Yeah, if you look at this, you see that actually we already have this formula. This is negative alpha x plus c1, and the c1 is this. So anyway, so if you want to find that, the equation is partial phi over partial x is negative 2 alpha x2 plus phi 2 minus phi 1 L plus alpha L2 equals 0. Okay, so if you solve this equation, then you can find the x max happens at phi 2 minus phi 1 alpha L plus L square, plus L, the half of L. Okay, so this is the location of the groundwater divide. So technically, using this, you can go and actually solve a very interesting problem. Say that this amount of water will go from the farm to the stream. This goes from the farm to the lake, or so many. Now you can go and actually interpret the solution and get much more information and knowledge about what's going on between these two surface water bodies. So this was just a very simple, interesting problem that I just wanted to solve for you, and you'll see in the homework problems you're going to play with similar problems like this. And as the final things that I would like to mention is that technically, based upon the problems that you have, you can go and pick a 3D or 2D or 1D problems. And it's very important that don't think that the 1D problems are useless, or that they are not as good as a 2D, or the same thing, 2D is for example, 3D is always better than 2D. So everything depends on the conceptual model that you've already created, and the conceptual model, that actually depends on the question. So questions that you have. So in some cases, it is much better to use 1D. In some cases, we want to use 2D, and in some cases, we want to use 3D. So we, as a modeler, we need to decide which model is the best one, and don't underestimate 1D, 2D model. So there, you can go and solve very, very interesting and practical problems using 1D and 2D systems, as what we did in this specific example. So I want to stop here. For next sessions, I will go and talk about a 2D unconfined groundwater flow. Okay, be safe.